The electron energy in hydrogen atom is given by En. I'm given the formula. Now, I already know the formula, but then they are feeling like supplying us the formula. Let them. En is minus 2.18 into 10 to minus 18 by n square joules. Fine. Calculate the energy required to remove an electron completely from n is equal to 2 orbit. So, from 2, you are finally moving it to infinity. That is complete removal. You are moving it to infinity. Okay, that is the first part. And then what is the longest wavelength, blah, blah. We will see it later. First, let us solve the first part. What is the energy required to remove an electron from 2 to infinity? That means difference in energy is E infinity minus E2, which is, well, E naught z square by n square when n is equal to infinity minus E naught z square by n square when n is equal to 2. Now, the moment you put infinity in denominator, it becomes 0. So, this is 0 minus 0 minus E naught. So, let's take a look. What does it give me? E naught z square by 2 square. Which now z is hydrogen atom, z is 1. So, this is minus E naught by 4. And E naught has been given to me. How much is that? That is minus 2.18. Again, please note, minus 2.18. So, this is plus 2.18 into 10 raised to minus 18 by 4 joules. This electron energy in hydrogen atom, this is the energy, extra energy which will be required for ionization. Can I calculate that very easily? That is going to be how much? Well, 4 5s are 20, 21. So 18, 4 4s are 16. 5.45 into 10 raised to minus 19. Oh, am I right? Yes. So many joules. This is the first part. Calculate the energy required to remove an electron completely from n is equal to 4, n is equal to 2. This is the energy. Then they are saying the second part, what is the longest wavelength of light in centimeter that can be used to cause this transition? Now suddenly students start getting doubt. What is the meaning of longest wavelength? What does all this mean? Can we mug up a formula? No. You can mug up fine, but then first of all you have to imagine this physically, what exactly is happening. See, you have n is equal to 1, you have n is equal to 2, you have electron here, and you find that a photon falls here. This absorbs energy and this jumps up and goes to n is equal to infinity. Fine. This is what is happening, right? You also calculated the energy of this photon. Yes, we did. Fine, very good. Now the fun part is, when you say longest wavelength, see, it's like this. I have this marker, fine. If I just try some strength, it's a plastic marker, I can break it. Yes, I can. I have that energy. Now, if somebody much stronger than me tries to break it, they also can. If the entire, you can say a mountain falls on this, or big huge boulders fall on this, they can still break it, yes. See, there is a minimum energy required to break this marker, right? If you supply more energy, will it break? Yes, it will break. It will be a waste of energy, but nonetheless, it will be crushed, no doubt. In the same fashion, if you are supplying a minimum energy, can an electron go out? Yes. But if you supply more energy than that, can the electron still go out? Yes, it still can. It still can. And that extra energy will even stay with that electron which has run away. Fine. But if you supply more than a minimum energy, the electron can still be broken away, it can still be pulled away, right? But if you supply an energy which is less than the minimum, what is the minimum energy? This is the energy, we calculated. This is the energy difference from 2 to infinity. So at least give me this much energy so that electron can jump away. If I give you more, you can. It's something like, to buy maybe a chocolate. You need 100 rupees, fine. Now, if you have 500 rupees, can you still buy a chocolate? Yes, you can still buy that 100 rupees chocolate and you will be left with extra 400 rupees. That's okay. But can you get that chocolate? Yes. And you are still having extra. So what is the minimum money you need to get the chocolate? 100 rupees. Provided it's 100 rupee worth chocolate, right? So at the same, in the same fashion, when we are talking about this, it's the same story. Why are we using this term like longest wavelength? It is confusing. No, it is not confusing. All it means is longest wavelength means minimum energy. That much you should appreciate hc by lambda, Planck's quantum theory. Now, so when I'm talking about what is the minimum energy, why minimum? Because if I supply more energy, I can still pull away electron. I can. But if I give less energy than this, then the electron cannot be completely removed. So there is something called as a minimum energy, but there is nothing called as a maximum energy, because you can give entire universe's energy to this, still it can break away. Not a big deal, right? So minimum energy. Okay. And that is why we have longest wavelength. So lambda is E. Sorry. E is hc by lambda. Therefore, lambda is hc upon E. Yes. So lambda minimum, yeah, maximum is hc upon E minimum. You need minimum energy, and reciprocal of that, you'll get maximum wavelength. How much is H? 6.626 into 10 raised to minus 34. What is C? C is 3 into 10 raised to 8. By minimum energy, how much is that minimum energy? We calculated there. That was 5.45 into 10 raised to minus 19 joules. Now, H is, this is joules second, this is meters per second. So I can cancel all these units, right? Neat and clean, what do I get? I get 6.626 into 3 by 5.45, lovely numbers, into, now 19 goes up, 19 plus 8, 27, 27 and 34, that makes it 10 raised to minus 7 meters. Oh wow. Or something into 10 raised to minus 5 centimeter, because 1 meter is 100 centimeter, you can put that and you can get this number. If I solve this, how much is this? 6.626 into 3 is approx 20, 20 by 5 would be 4, 5.5 is a little less than 4. It's roughly 18 to 3.647. We have the answer also. So we have the final calculated number. Use it and be happy. That's it.